Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 12, Section 2 notes all over chemical calculations. So we're going to be talking a lot about mole ratios. And a mole ratio is a conversion factor derived from the coefficients of a balanced chemical equation interpreted in terms of moles. In chemical calculation, mole ratios are used to convert between a given number of moles of a reactant or product to moles of a different reactant or product. So let's look again at this balanced equation for the production of ammonia. We have N2 plus 3H2 yields 2NH3. So if we look at the 3 mole ratios we derive, we just are using their coefficients to make our mole ratios. So we can look at mole to mole calculations, and in the mole ratio below, W is the unknown wanted quantity and G is the given quantity. The values of A and B are the coefficients from the balanced equation. The general solution for a mole-to-mole problem is given by the following. Some X amount of moles of G times the mole-to-mole ratio of G to W. And when we multiply that through, we're left with just the moles of W. Remember that A and B are the coefficients that are respectively to G and W. So how many moles of NH3 are produced when 0.60 moles of nitrogen reacts with hydrogen? So let's write down our chemical equation that we just had on the previous slide. So we had NH2 plus 3H2 yields 2NH3. And we're going to start with what they tell us, just like we've done in the past. So 0.60 moles of nitrogen. And we want to get to, it says how many moles of NH3 are produced. So we're going to use that mole to mole ratio. So we're going to say 1 mole of nitrogen for every 2 moles of NH3. We can make sure that our units cancel out properly, and they do. And we multiply that through, and we get 1.2 moles of NH3. So we also have mass-to-mass calculations. And if a given sample is measured in grams, then the mass can be converted to moles by using the molar mass. Then the mole ratio from the balanced equation can be used to calculate the number of moles of the unknown. And if it is the mass of the unknown that needs to be determined, the number of moles of the unknown can be multiplied by the molar mass, which we've done in the past. So a mass-to-mass calculation looks something like this. The mass of G, and we use the molar mass of G to convert to moles, and then we use the moles of G, multiply that by the mole-to-mole ratio of G to W, then use our molar mass of W, and we end up with the mass of W in grams. So let's calculate the mass of a product. This question says, calculate the number of grams of NH3 produced by the reaction of 5.4 grams of hydrogen with an excess of nitrogen. So just like we have been doing, we start with what we know. So we're going to start with 5.4 grams of hydrogen. And they want to know how many grams of NH3. So we're going to use the molar mass of H2. And remember, it's H2, so it's going to be 2.02 grams of H2 for every mole of H2. Now here we're going to use our new piece, and that's going to be our mole-to-mole ratio. So 3 moles of H2 for every 2 moles of NH3. And now we need to multiply by the molar mass of NH3. 17.04 grams of NH3 for every 1 mole of NH3. So let's go back through, make sure our units cancel out, and we end up with what we want. Gram H2, mole of H2, mole of H2. Mole of NH3 with a mole of NH3, and we're left with grams of NH3, and that's what the question's asking us for, so we must have set this up right. When we multiply that through, we get 30.4 grams of NH3. So there are 30.4 grams of NH3 produced by the reaction of 5.4 grams of hydrogen with an excess of nitrogen. So in a typical stoichiometric problem, the given quantity is first converted to moles, and then the mole ratio from the balanced equation is used to calculate the number of moles of that wanted substance. Finally, the moles are converted to any other unit of measurement related to the unit mole, and as the problem requires. So if they're asking for atoms or molecules or even liters, we can do all that because we have conversion factors from those two moles. So this is a little skeleton of the types of equations that we're going to be looking at. You can go from representative particles of G, mass of G, volume of G, to those same units of W, all using the mole-to-mole ratio in the middle. How many molecules of oxygen are produced when 29.2 grams of water is decomposed by electrolysis according to this balanced equation? So we're going to start with what they give us. So 29.2 grams of water. And they want to know how many molecules of oxygen. So the first thing we need to do is use the molar mass of water to get to the moles of water. And now we use our new piece, that mole to mole ratio, and we have 2 moles of water for every 1 mole of O2. And we know that there are how many molecules of O2 in a mole? This should come right off the top of your head. There are 6.022 times 10 to the 23rd. That is a 23, I promise. Molecules of O2 for every 1 mole of O2. We're going to have to write our answer down here. So we multiply that all through, and we are left with 4.88 times 10 to the 23 molecules of O2. We can also do this for volume. So we have nitrogen monoxide and oxygen gas. They combine to form the brown gas nitrogen dioxide, which contributes to photochemical smog. How many liters of nitrogen dioxide are produced when 34 liters of oxygen react with an excess of nitrogen monoxide? So again, we start with what they tell us. 34 liters of oxygen, and we are trying to get to the liters of NO2. So we know that there are 22.4 liters of O2 for every 1 mole of O2. And our mole-to-mole ratio is 1 mole of O2 for every 2 moles of NO2. And then we also know that there are 22.4 liters of NO2 for every 1 mole of NO2. So if we go back through, cancel out our units, make sure we're doing this right. Everything cancels out, and we're left with just liters of NO2, which is what we're looking for. Multiply that through, and we get 68 liters of NO2. So assuming STP, how many milliliters of oxygen are needed to produce 20.4 milliliters of SO3 according to this balanced equation? So we start with what we know, just like we've been doing. 20.4 milliliters of SO3. And now we know that there are 22.4 liters for every 1 mole. So we need to convert our milliliters to liters. There are 1,000 milliliters for every 1 liter. And there are 22.4 liters of SO3 for every 1 mole of SO3. Now we've come to our mole-to-mole ratio. 2 moles of SO3 for every 1 mole of, sorry about that, for every 1 mole of O2. And now we're looking for the milliliters of O2. So we start with moles of O2. and we say 22.4 liters of O2 for every 1 mole of O2. We multiply that by 1,000 milliliters. Sorry, that looks really terrible. 1,000 milliliters for every 1 liter of O2. Multiply that through. Check through that our units cancel out again. Just make sure we're doing this right. Mole and mole, mole O2, liter of O2, liter of O2. We're left with the milliliters of O2. We multiply that through and we get 10.2 milliliters of O2. Alright, so in review, in chemical calculations, mole ratios are used to convert between moles of a reactant and moles of a product, between moles of reactants, or between moles of products. We can go between any of the 4 or however many pieces of information are in our chemical equation. In a typical stoichiometric problem, the given quantity is first converted to moles, then the mole ratio from the balanced equation is used to calculate the moles of the wanted substance, and then finally, the moles are converted to any other unit of measurement related to the unit mole. Alright guys, I know that was a long one with a lot of math, but we're going to get a lot of practice with this. As always, all the information on these slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook, the resources CD, and pearsonchemistry.com. Have a good day, guys.